Hello, my name is Michael Hansen and I'm ready with one more of my answers to Brian Mullin's videos. So in this video I would like to address Brian Mullin's fourth video where he talks about the ISS, satellites and the thermosphere. Now his general claim is that because we have satellites and the ISS in the thermosphere where the temperature is hot, something around 1800 Kelvin, it would seem to him strange that the ISS, which is made of metal, aluminium, where the melting point of aluminium is way below this temperature, and we have plastic and all sorts of other special interesting things on those satellites and the ISS. Why does it melt? Why doesn't the people up there boil, and so on and so on? Alright, he also makes some other claims, and I will take them as we go forward. So the first thing we have to address here is we have to look at the ideal gas equation and kinetic gas theory. Now he made some statements about the first and second law of thermodynamics, and those are correct. I actually also had to pull out one of my old books in order to get the thing back, because thermal physics or thermodynamics is something that's taught as a first year student, so it's a little while back. All right. So let's look at the gas equation. I'll put it up here. The gas equation, as a chemist would like it, it's the pressure times the volume is equal to the number of moles times the constant times the temperature. Alright? I can't remember the name of that constant. So what would a physicist do, because we are more interested in the number of particles, in the number of molecules. So we know that in 1 mole we have Avogadro's number, or Avogadro's constant. It's something 10 to the 23rd, so it's a lot of particles. And then we have the number of moles, right? It makes sense. How many particles do we have in a box? Well, we have how many particles there is in a mole, and then the number of moles we have. So So moles, number of moles, little n times the Avogadro's number, which is particles inside a mole, gives us the total number of particles. So in order to replace that little n, we just move a little around and get big N over Na, or Avogadro's number. So I have just written this part here, I've done this, alright? So we get N over Na times R times T. And then we make a new constant, where we say that Boltzmann constant is equal to R over Na, and it's something like 10 to the minus 23rd. So it's easier to calculate when using a small calculator like this, for example. This really doesn't like big numbers, really big numbers, so it will get an overflow. So what we're left with is P times the pressure times the volume is equal to the number of particles times Boltzmann constant times the temperature. Alright, so let's try to make a statement about the temperature. So what can we do? Well, we can move around a little bit. So we get the temperature is equal to the pressure times the volume divided by the number of particles times Boltzmann's constant. And if we set the pressure and the volume to be constant, and of course Boltzmann constant is constant, we can say that the temperature is proportional to 1 over the number of particles. So what does that mean? That means if I have a box with particles, where these particles have a specific energy distribution, right? If I load a lot of more particles into that box, and the pressure and the volume is constant, then let's do like this. the temperature will drop, will go down. So why is that? Well, let's say that I have these particles moving really fast in there. So one of the ideas of thermodynamics is that we can say that kinetic energy of a particle is proportional to the temperature, right? So if I have a box of particles and then put temperature into them, give them energy, they will move faster. If I take temperature out or energy out of them, if I try to cool them down, they will move slower. Now, one special example which I wrote about in high school is what's called a Bose-Einstein Condensate. And so this is made by, it's called ultra-cooling atoms. So you trap atoms inside a trap, a laser trap and a magnetic trap, and then the particles, the atoms is almost, they're not moving very much, they're very slow. So the energy will go down. The temperature goes down, so we are down in the microkelvin area. Very, very cool. Ultra-cooled atoms. So that's how it works, right? And so in this case, I have the number of particles I originally put in there, they have a certain energy. And then I dump a mother load of other particles in there. They have to share that energy because the box is perfectly isolated, so no energy gets out and no energy comes into the box, and they have to share it. And if they have to share the energy between more particles, the temperature, the average temperature, will drop. Alright? So this can sort of explain or give an idea about how come this temperature could be 1800 Kelvin, that's pretty high, and the temperature here is 170 Kelvin, which is pretty low, right? And this is sort of how to try to reenact what Brian Mullin draw on his blackboard or whiteboard. Alright, so one of the questions that he comes up with is, well, if you have a satellite here, right, and the temperature in the thermosphere is that high, why doesn't the satellite melt or becomes heated up? So first of all, we have to look at kinetic gas theory, right? So the first thing is that how is energy transferred between anything actually. We have two possibilities. We have the collision between particles. Oh, sorry. So we are transferring kinetic energy here. The other possibility is that we have a particle here and then we irradiate it by a photon, right? So what goes on here? Well, these particles are irradiated by the sun, and that is why they are so extremely, because they are few, density is low, and they are irradiated by the sun. Every time a particle gets hit by a photon, I would say probably an ultraviolet photon, because they are very energetic. I'm not sure about that, but that would be my guess. They will transfer the energy to this particle and speed it up. So why doesn't this happen to this one here, the satellite? Well, first of all, let's just say that, as Brian Mullin states, the transfer of kinetic energy from these particles to the satellite is not very likely, because the density is very low. So you can say that the average temperature in the thermosphere is somewhere around 1800 Kelvin. But the energy of one single particle is definitely not enough to heat up this entire satellite to, well, 1800 Kelvin or that much. and because the density is very low, it doesn't happen that often. So, but what is correct is that the radiation from the sun comes in at both the particles and the satellite. So, in order to address this question here, I actually have to go forward with another question that Brian Mullin asked, is that, let's take for instance the lunar model on a typical, one of the typical lunar missions, and just take the one where they don't land on the moon, but it doesn't really matter whether they land or not. So how come it be, he asks, that the lunar model is not heated up by the radiation of the sun, but it radiates energy? How come it can give energy outward to space and not receive it from the sun? And the answer to that question is that one possible answer, the best one I can give, is that we have to look at what kind of radiation we're talking about. So the sun radiates in what we call actually a broad range of electromagnetic waves, but in general what we are interested in is the part of the ultraviolet and the infrared, and then the visible part of the spectrum. Now, in our atmosphere, most of the ultraviolet part is blocked out. There's a small amount that comes down that is hurtful to our skin if we are exposed to the sun for too long time. And then also a part is infrared, but I would say most of the part is probably the visible part. So what happens when? Now let's just state what goes on with a human being, because obviously when I look at another human being here, he's not bright, he's not emitting light in the visible part of the spectrum, but humans actually also glow in the dark. We just do it in infrared, or heat. Some would call it heat radiation, but in reality it's not heat radiation, it's infrared radiation. We are a glowing light bulb, just glowing in infrared. Alright? So what happens? Here's the Earth, here's the Sun. So what happens when we have clouds here? So, and we have, let's just say we have the atmosphere here, but it's not really correct, right? But let's just for simplicity say that we have, this is the ozone layer. So when we have an ultraviolet ray, we would say that most of it is reflected out and a small part goes through. Visible light, all the visible light goes through, right? Let's call that V. And then we have infrared, IR. This is also reflected by clouds. Now this is sort of a basic idea how you would perform a very simple atmospheric model of the Earth, and energy transfer system, how much energy comes in and how much energy is radiated out. What happens when visible light hits the Earth? But actually, some of it is reflected back, right? Let's make this smaller. Some of it is reflected back, but most of it is transferred into infrared radiation, which is reflected back by clouds. So as the clouds will, and also parts of the upper atmosphere, water molecules and so on, as the infrared radiation is radiated or reflected outwards by the clouds, so will the infrared radiation coming from the Earth be reflected back by clouds. The visible light will go out, and that's what we call the Earth albedo. It's very low, I think it's a couple of percent that's radiated. So most of the radiation that comes down in visible light and isn't trapped up in our atmosphere will be converted to infrared energy. So what happens inside? Let's see if I can draw a lunar model. Something like this, right? And two big windows here. Alright, so the person standing, let's just draw a little person here. The person inside the lunar model, it's radiating in infrared. Now, even though we made this, let's say that for argument's sake that this, what covers the lunar model both on the inside and the outside, re-radiates something about, let's say 95%. It's reflected. Alright? It's probably something lower, but in any way. Because what comes from the sun mostly is in the visible part of the spectrum, we can make the lunar model so it will reflect the sun out, the light from the sun outwards. So we have visible light coming here, which is reflected out again, right? But as this person sit in here and we have this infrared being reflected around in there, at some point this material that covers this aluminium will be heated up, just slightly, but enough that the lunar model itself will radiate infrared out into space. So the reason why the lunar model won't be heated up by the sun's radiation, it's because it reflects the visible light out back into space. But the reason why it gets cold in here when they turn off the heater, like they did in the film Apollo 13 that Brian Mullin also mentions, is that the lunar model itself will radiate infrared radiation out into space. So we don't need the collision between particles in order to cool down an object in space. We need it to radiate infrared radiation out into space. So even though we say that 95% of the infrared radiation is kept inside this lunar model, when you turn off the heater and you only have the human body, it will cool down. It's just a matter of time. Okay? So that's the part of the thing about it. And the same goes on here with the satellite. Now, one of the things he mentions is that why aren't the solar panels, why doesn't the solar panel transfer heat to the satellite or to the ISS? Why isn't that happening? Well, the first explanation could be that you could, let's say that you have a solar panel here. Then you could put something in here that's a bad conductor to the satellite or to the ISS. That's one possibility. So this will have a temperature, let's say this is temperature 1, but this will have another temperature because this part here doesn't conduct heat that easily. He mentions an iron rod, right? It's perfectly correct that if you take an iron rod like this and heat it up here by a flame, then the heat will transfer pretty quickly down to this part. But let's say we put an insulating matter between, then this part will get heated very much up very much, but this will not. not nearly as much. Another possibility, which I think is the most correct explanation, is that a solar panel takes the radiation from the sun and converts it into electrical energy. Now, if the radiation from the sun is converted into electrical energy, it cannot also be converted into thermal energy. So that's not a possibility, right? So even though this is really trapping, really absorbing solar radiation, it's not just said. You cannot just say that this will be converted into thermal energy when it's also converted into electrical energy. It has to be the other way around, right? It has to be either. It cannot be converted into both the same amount of energy. The same amount of solar energy cannot be converted into both thermal energy and electrical energy. It has to be a portion of each, right? So if you say that, well, if 80% of the energy hitting the solar panels is converted into electrical energy, let's call it EL, then we have about 20% that is converted into, let's just call it kinetic energy, but in reality we also call it thermal energy, right? And remember that this thermal energy will be infrared radiation, and that means that these solar panels will also radiate in IR, in infrared, when they are heated up. The last thing he mentions is, and I will erase all I have here, is some astronaut being shown from the ISS to turn about his own axis. So let's look at what happens on Earth when we are just standing here, right? So I'll draw a person here. Big arm. And then we have the gravity pulling down. What does this mean? It means that if we didn't have our veins have a small valve that when the blood comes in here and goes through the valve, when the heart beats, it cannot go back. It stays there. This is only in the veins, it's not in the arteries, right? Because if we didn't have that, we would have almost all our blood down in our legs and almost nothing up here in the head, which would be bad, because then we would be not having it so well, right? That is also why, what I've been told, that fighter pilots have to train themselves into tightening all their muscles in the leg and the stomach in order to keep the blood from flowing down when they're doing a high G turn, and that will cause a blackout. And the reverse also happens when they make a nosedive, a quick nosedive. All the blood will rise up to the head, and they will get a redout. Now, I'm not sure you can prevent the redout. I'm not that into fighter piloting, but I know that you can prevent the blackout by tightening your muscles and keeping the G value, the big G, and the pull on the blood to a certain value. Alright, but in space, try to make the same person again. Now, we are weightless, but we're still feeling the pull of gravity, alright? So we still have some pull of gravity. But let's just take the situation he mentions where the person turns about himself. So I'm going to try to draw him from the side. So he turns like this, he spins around his own center of axis. So that means that when you do that, when you spin yourself around like this, your body will experience a centrifugal force going outwards. That means that the blood will be pulled towards the head and towards the legs. And that could possibly explain why he gets red in the head when he does that. And besides, if he's using, because there's no real tug of gravity pulling the blood down in that sense, right? If he tightens his muscles doing this, he will also press the blood out up to the head, right? Because when you tighten your muscles all around in your body, then unless you have really extremely strong facial muscles, they will not be able to push the blood back down again. So this is a possible explanation why he gets a red head when he does that. Alright, I think that's all I have about the video he does about the ISS. So just to recap, the reason why a space station or satellite doesn't boil in space, even though the temperature in the thermosphere is extremely high, is because the density of particles in order to transfer this energy is very low. And also because the satellites and the ISS is made in such a way that they will reflect most of the light coming from the sun, and that in that way will not convert this, like for instance with the Earth, in the visible light hitting the Earth will be converted into thermal energy, or you can call it infrared radiation. And because we have a layer of clouds over the Earth and also part of the atmosphere, the infrared radiation will be reflected back towards the Earth, but the visible light will go straight out, and that's the Earth albedo. But the reason why a space station without a heater or a lunar model or a satellite, maybe satellite is not that important, but at least things with human inside, the reason why they can become cooler, the temperature can drop in outer space when we don't have a heater going or some other source of heat, is because the space station itself and the lunar model will be heated up by the humans inside. We will transfer energy to the lunar model, and as the lunar model gets heated up just slightly, not much but slightly, it will radiate infrared radiation out into the atmosphere, out into space, just like the Earth does. But because you don't have a layer of clouds around neither the infrared, the space station or the lunar model, the radiation will continue out into space. So that's the explanation. And the third thing, as he mentions, the reason why you can, I will say, I cannot say it for sure, but my explanation for him getting red in his head when he's turning around in space could be that either he's a combination that he's tightening his muscle in order to do that, then he will press the blood up into the head. And the other explanation is that he's simply turning around his own center of axis, center of gravity, or whatever you would call it, rotation center, and the centrifugal force his blood will experience will push it out towards the head and the feet.